Hello friends, welcome to my channel. Let's have a look at problem 333, largest binary search tree, subtree. In this video, we're going to share two treatments for this problem. The first one is more verbose and with some redundancy, and the second one is more succinct. First, I'll read through the statement to digest the problem requirements, and then we do the analysis, and finally we share the code and explain the codes line by line. First, the statement. Given the root of a binary tree, find the largest subtree, which is also a binary search tree, where the largest means subtree has the largest number of nodes. So next, in the statement, it's a definition of binary search tree. I will not repeat that. So here is a note. A subtree must include all of its descendants. So actually this is an important assumption. So we are not considering a piece, but we consider all the descendants. So with that said, let's look at example 1. So in example 1, so we have the return should be 3. So we cannot include a 10. For example, 10, 5, 1, 8 is also a binary search tree if we do not consider 15 and 7. However, if we add 7 into the tree, so the whole tree is not a binary search tree. But the problem requirement is that a subtree must include all of its descendants. So the tree represented by the root 10 is not a binary search tree. So the maximum size here is 3, not 5. So 5 means we can include 10 and 15, right? So this is example 1. So similarly, you can analyze example 2. So with that said, let's also look at the constraints. First, the number of nodes in the tree is in the range between 0 and 10 to the power 4. So in particular, it tells us that so the tree can be a null tree. Secondly, the node value is in between negative 10 to the power 4 and positive 10 to the power 4. In other words, so the node value can be 0 or can be negative. So here is a follow-up. Can you figure out ways to solve it with ON time complexity, right? So with that said, let's look at the treatment. So here I'm going to share two treatments. First, I'm going to write a binary search tree checker. So and also a nodes counter, and then we use them to do the job when we traverse the tree. So this actually is meant to help us understand the finer details and the overall logic. And in the second treatment, we're going to write a compact format of treatment 1. So actually, it can be very short. So notice that for a binary tree to be a binary search tree, so the binary search property should be valid for recursively. In other words, for all the subtrees. So let me delete this form. So with that said, we are ready to do the coding. So first, I'm focusing on treatment 1. So in other words, I'm going to write with some redundancy. So write with redundancy. But this is important for us to understand the finer details. So here I'm going to use 3 steps. First, so I'm going to write a BST checker. So to save us some typing, I'm going to call this function f. So the f will accept a root or node, tree node, and a lower bound and upper bound for the binary search tree. See, I'm going to initialize it using negative infinity and float positive infinity, right? So let's call this high, right? So with that done, so we actually can do the checker. So first, if not root. So in this case, we're going to regard this as an empty binary search tree. So we're going to return true. So more or less, we regard more. So we regard this as a base case or stop condition. So otherwise, so then we check if the root value is in between the low and high, strictly, right? So less than high. If this is the case, and also the left subtree and the right subtree are binary search trees with proper bound, then we're going to return true. So here let's look at the root left. So we hope that the low remains the same. However, the high should be less than the root value. So we're going to set this high to the root value, right? And also we need similar thing for the right subtree. However, for the right subtree, the low should be larger than the root value, and the high remains the same as previous. So in this case, so we're going to return true. So notice that here are some two recursive calls. So all the other cases we're going to return false. So this function f is a binary search tree checker, right? It's going to check if given a tree node, we are going to check if the tree represented by that node is a binary search tree. So this is the first part. The second part is a simple one. So it's I'm going to write a number of nodes, node counter. So nodes counter. So this can be done also recursively, very easy. So let's call it G, just for saving some typing. So given the root, so we're going to return a number, right? So first a stop condition or base case. If not root, so we're going to return 0, right? So otherwise, so we're going to return 1. So this is counting the root node itself, and then we count the number of nodes in the left subtree and the right subtree. So G root left and plus G root right. So this actually needs a traverse again. So that's why we see that this way of writing the code and do the problem logic has some redundancy. But it's good to understand the details as we mentioned. So this is the second step. The third step is traversal and check, right? Check and count. So for this, I'm going to initialize a result variable, right? So let me first treat a special case, if not root. So it's possible due to the problem assumption. So we're going to return 0. And then we're going to consider generic case. So we're going to initialize a result variable, counting the size. So because the smallest size is 0, right? So we initialize it with 0. And then we are going to initialize a stack. So we're going to do a pre-order traversal maybe. So any traversal will be fine. So for this problem, so here val s. So I'm going to get node equals s pop, and then we're going to check if this tree represented by node is a valid binary search tree. In other words, we need to consider all of its descendants. So if this is the case, so result is going to be maximum of result and G node, right? We're going to count the number node. So this is the case. So this part actually is the problem logic. So if we ignore this if, and then we check if node right. So we're going to put this node right into stack. So if node left, so we're going to append this to node left. So this is the logic for pre-order traversal. So afterwards, so once we finish this while loop, so we can return result state. So this is one way of doing the code. So actually this is very verbose. However, if we could implement all of this using from scratch, that's also a good thing. So with that said, let's first do a check. Yeah, it passes the first example. So now let's look at the second, the generic case. Yeah, it passes all the cases. So now we have gained some intuition with this version of code. So now let's look at the second version. I'm going to copy this function signature and change this one to be v1. And now let's look at here, so the short version. So for this, again, I'm going to write a hyper function, and then we're going to get the bounds of the binary search tree corresponding to a node, and also we want to count the number of nodes or the size of that binary search tree. So first, let's write the hyperfunction. So so for this hyperfunction, so I'm going to define it as DFS maybe. So I'm going to call it node. So this function is going to return a number of information, 3 pieces of information. First is the maximal BST size. So in the tree represented by node, maybe it's the size of its subtree, but that anyway, the maximal BST size. And another one is that the left bound. If we look at this tree for this node, and represented by this node, and the right bound. So similar as above, but we need some special treatment to make connections. First, if not node. So in this case, so actually we shall return 0. In other words, there's the 0. We regard this one as a valid binary search tree. But the left bound will be, we're going to set it to be positive infinity, and the right bound, the larger one, we're going to set it to be negative infinity. So here, the reason we set it to be positive infinity and negative infinity, so you can think of this corresponds to an empty set in mathematics. Then you can understand why we set it to be positive infinity and negative infinity respectively. So this corresponds to min, this corresponds to max, right? Or left lower bound or upper bound. So this is the case. So next we're going to track the information for the left subtree and the right subtree. So left subtree size, binary tree size, and the left min and the left max. That's going to be DFS, node left. And similarly, we do for the right number of nodes. So right min and the right max is going to be DFS, node right. Then we want to make connections for these two. So we are going to check if node value is strictly in between the left min, left max, and the R min, right? So left max, R min. So in other words, what we intended to incorporate is that the current node value is larger than the largest value in the left subtree and less than the smallest value in the right subtree, right? In this case, so we're going to get the size of the tree. It's going to be, so this tree should be noted at node currently. So 1 plus left number plus right number. And then we're going to set the min and max. But notice that this not guarantee that this whole tree is a binary search tree. So we want to set min to be the left min and the node value. Similarly, the max will be right max and node value. So if we look at the else block, then we could understand why we write like min and max here, right? So in other words, if the tree rooted at node is not a binary search tree, still we can get the number of maximal binary search size within this tree represented by the node. So in other words, the left subtree may contain valid binary search tree, and the right subtree may contain the valid binary search tree. So in this case, so we're going to have left number on number, so the maximum. So then we're going to set float negative infinity and float positive infinity. So notice that, so if this two components in the return, this negative infinity and positive infinity, it indicates that the current tree represented by the node is not a valid binary search tree. So we write the left bound to be negative infinity and the right bound to be positive infinity. So this is to be distinguished with the first stop condition. If we have an empty node or null tree, so we regard it as a binary search tree. However, so here the number node is 0, but the float, the left bound is positive infinity and the right bound is negative infinity. So this way, actually, we can make this connected, right? So the thing is that, if this condition holds and both the left subtree and the right subtree are not valid binary search tree, so in this case, we're going to have this in the left subtree or right subtree. Left subtree will have the second component, L min, will be negative infinity. So we get negative infinity here also, and we get max and positive infinity here also. It indicates that the tree at here is not a valid binary search tree. So this way, due to the use or properly setting of positive infinity and negative infinity, so we could mimic the Boolean function here in the first solution. So the second solution format is very short. So now with that done, so we can do the function call and return. So we just need to return DFS root. So we're going to return 0, right? So this second version actually is a compact format of the first version. So with that said, I guess we can do a check first. Yeah, it passes the first example. Now let's look at the second example, the generic case. Yeah, it passes all the cases. So here, up to now, we finished the sharing of the two formats of code or the two treatments. So here, before we end this video, let's make a extension. So in the problem, so we are required to consider all of its descendants. In other words, so we cannot consider 10 and 15. So how about we relax or remove the assumption that we need let's see, this one, right? So if we remove this assumption, then in the example 1, the output should be 5. The largest binary search tree will be rooted at 10, and the left subtree is marked by blue, and the right subtree will be ending at 15, right? So this is the 5. So can you tune or tweak the code to write a solution for the latter, right? So with that said, I guess that's it about this video. Thank you.